Okay. Might be too loud. So today we're gonna do 3 sum. This one I have not done before. I think I'm 2 away from finishing 2 pointers. Yeah, so the goal is to do 3 sum and then do trapping rainwater. But we'll see how far I can get. Also, if the music's louder, I can't tell if the music's louder than my mic. Anyways. So let's read the problem first. What do they want us to return? So we get a vector of integers. And we're supposed to return all the triplets that sum to what? That sum to 0? Okay, there's no target. Okay, so we can't repeat the same indices. They all have to be unique. And okay, the order does not matter. Let's see at the example. So nums has 6 elements. And one of the outputs is -1, -1, and 2. Wait, are we returning the indices? The indices? It looks like we're actually returning the values. As long as the indices are not the same. Okay. So for the first one, nums at index 0 is -1. nums at 1 is 0. And nums at 2 is 1. That sums to 0. And let's see, the other option is index 1, 2, and 4. So 1 is 0, 2 is 1, and 4 is negative 1. But they don't add it to the output because there's already one similar to that. It's just flipped. Okay. Okay, another solution is index 0, 3, 4. 0 and 3. Wait, 3? Right. So 0 is negative 1 plus index 4, which is negative 1, gives us negative 2, plus index 3, which is 2, gives us 0. Okay, 2 pointers. Sorting. Okay, so we should start whiteboarding. Do a timer. 15. Okay, let's see. How can we do this? Space, we can use 2 pointers. Yep, we have 1 pointer there. Negative 1 in our vector. We have 2 empty spots. Okay, our second pointer. Our second pointer will tell us what we're missing. So if we do The only value that can fit here is 1. So then we can have the pointer traverse the rest of the array looking for 1. And if it finds it, we can put it in the vector. If it doesn't find it, then we can move the pointer up by 1. Then this would become that's already 0. The only value that can go here is 0. We could search the rest of the array looking for 0. If it does not find it, we'll do the same thing. Okay, so we know it won't find that 0. Okay, but the 0's here. So it should find 0. Oh, well, we already would have had a pair, right? So previously it was here, the pointer, and it would have found 1. Then if we move the right pointer down, we're looking for 0. If we traverse it from the beginning, we will find 0 here. These values flip. Essentially, they're still the same set of values that are in this vector. There's no reason to make that a pair or a triplet. A tuple, is that what it's called? Anyways, we can do without. We already have that case. See, if we do this one, we're looking for 1, but 1 won't be here. We miss this one here. Was that a pair in the example? I think it was. Wait a minute. We're not looking for 1, sorry. Yeah, so we start at 2. We have -1 and 2. So we're looking for -1. Which would be 1 over. Let's see. Go 1 over. We have -1. We would have already had this pair. So we can kind of do without. This would have been -2. We're looking for this 2, but it does not exist after. Either way, if we start the loop from the beginning to look for the 2, we would have already made that pair. Just in a different position. It would have been, it goes 2, -1 previously. I don't think this is right. How does the 2-pointer solve this? See. Two-pointers usually go like this. We have one in the beginning and the other one at the end. And you essentially move them towards each other. I'm trying to think, in what case do we move them towards each other? Okay, let's see. Do you need 3-pointers? Okay, well, it's not sorted. Doesn't really help our case. Okay. Wait, how would I solve this? I could do a map, and we can place all the values and their indexes. So let's say their values are indexes. So we can do like -1. That wouldn't really make sense actually. It'd probably be the other way. Probably the indexes as keys. I think this makes it slower though. Okay, if we put them in a map, we can then iterate through it. We'll need a function. I'm trying to think what the equation is. So for the index, so on an I, this one's -1. We can do like, so 0, and then the index plus -1. So then we're looking for 1 to get to 0. It doesn't always have to have 1 though. I mean, sorry, it doesn't always have to have 0. That assumption's wrong. Let's see. I cannot think of the solution for this. I might have to look at the tips. Also, my time's up, so let's look at the tips. There's 5 hints. Nice. Okay. Okay, we could sort it. Wait a minute. It says we can do it in place. That's a hint on its own. Sorting is not in place, bro. Is it considered in place? Actually, I think it is. Okay, hint 3. Yeah, I don't think I could solve this. This crazy headache too. I don't think I could solve this. I'm just staring at this and I cannot even think of a solution here. Okay, I'm so confused. What does it say about sorting? How does that? Sorting the array. Okay, why don't we sort it in the whiteboard and we'll see. Does it reveal anything? What does this reveal? What was the other hint? See. Can we iterate through nums with index I and get? Okay, let's say this is I. And the equation he's showing is equal to negative left plus right pointer of the sorted array, I'm assuming. I'm not too sure. Wait, but now it's sorted, so it wouldn't be. This would be J here. It says we can iterate through nums with index I. This is nums, but sorted. We have I. And then J and K, where J is the left pointer. Wait, do we start J in the same position without duplicates? So maybe it would be here. Something like that. But then for some reason he turns this one negative. Cross that out. Okay, that one's valid. But then how do you move the other ones? Okay, if we move I up by 1, this would have been a valid pair, right? So I did that wrong. Like I butchered it. Okay, it's missing one. Okay, I'm gonna watch the video. I'm not sure what I'm doing wrong here. So this is sorted. We're gonna iterate through it with I, and then we have a left and right pointer, but the pointers never overlap in the same index. It does catch the one correct output, but it doesn't catch the other one. So maybe we should look at the video.
Okay, let's solve Leetcode.
Super loud.
15, three-sum, the sequel to the popular question two-sum. So before you solve this question, the first thing you should do is make sure that you've solved two-sum, which is the most popular question on Leetcode, so you've probably solved it or at least seen it before. I also recommend solving two-sum 2, which is basically two-sum except the input array is sorted. A lot of people skip this question. I think that's what makes three-sum a little harder because they don't solve this one first. If you solve two-sum and two-sum 2, this question three-sum is pretty straightforward in my opinion. But okay, let's get into the question. So we're given an input array of n integers as per usual. This array, though, can have duplicates as we can see in the example, right? 2 negative 1s in this case. Now what we want to do is find three numbers of this array, so A, B, and C, and we want them to sum to 0. So in the example, there were two elements, 0. Now one problem is that we cannot have duplicates in our solution. So we're going to have to keep that in the back of our minds. So let's just start the most brute force way. We see that we need three numbers, so why not just have a triple loop, right? Just get every single combination of three numbers. That's probably the first thing you're going to try, right? So let's say our first number is negative 3. This is our A. So to come after it so that it's a C. Now, if we did that with our triple loop, we would find that there is one such combination starting with negative 3 that will sum to 0. If we take 1 as our B and we take 2 as our C value, because then we'll have negative 3 plus 1 plus 2, that's obviously 0. So to our solution set, we can say, okay, there's a negative 3, a 1, and a 2. So now when we move, we can consider this as our first element, right? But eventually we'll see that we go through the entire thing and we don't find anything that can be added to 3 that'll give us a sum of 0. We'll do the same for this one and there isn't anything. Now we get to a negative 3 again though, because remember there are duplicates in this array. So now we're saying again that we're going to put negative 3 in this first spot. Now this is a recipe for finding duplicates. This is not good. And we'll see in this example, that's exactly what's going to happen. There's another, we'll take this as our B, we'll take this as our C. Again, we find negative 3 plus 1 plus 2 sums to 0. So then we're going to add that again to our result set, right? But that's not what we want.
So is it, okay, we're assuming that A is the first loop, and then we have two more loops, right? That are one index ahead. So let's see. If A was here, how would we find a B? We would have to start the loop from index 1. And this is the weird part to me, because how would you know? Let's see. If you had an inner loop, we could check index 1, that sums to 0. Obviously, nothing else would matter at that point. So you continue 4. It gives us 1. So we're looking for 1. But then we have another inner loop. That starts 1 index ahead from index 2, looking for 1. Sorry, negative 1. It's not going to find that. So then we can move A by 1. So then we have 3. Then the second inner loop, we'll be looking for, well, I'm not too sure actually. I mean, we know it's 1 and 2.
We want to eliminate the duplicates. So the problem was we took -3 as our A value, right? And then we searched the rest of the array for two numbers, 1 and 2, that add to 0. But then we went back here, right? And we found the -3 again, and we did the exact same thing. The problem is we don't want to have the same number in this position, in the A position, twice, because then if there are the numbers that come after it, we could potentially find duplicates. The solution to this problem is to sort the input array. Let me show you what I mean. So here you can see that the array is now sorted. Let's cross out our top array, which was unsorted. So now we are going to sort the input array. So now when we're looking for all combinations, if we find -3 first, then that's good. Okay, we'll say -3, then we find these two numbers, 1 plus 2, and then we find our solution. Great. Now if we get to -3 again, we'll say, hey, wait a minute. This number was already in this position, right? And we know that because its neighbor, its left neighbor, is the same value. We don't want to put it twice here, because if we do, we'll get the same duplicate. So we're going to tell ourselves that we already computed all combinations that start with a -3, so we don't need to do that anymore. We already visited this one. We're going to skip this one, and then we're going to go here. So that means in this case, we're not going to find any more results in the remaining portion of the array because they're all positive. They're never going to sum to 0. So then in our result, we're only going to have the one triplet, -3, 1, and 2. We eliminated duplicates by not reusing the same element twice. I think it helps to understand a little bit about the statistics of like combinations and permutations to like understand exactly why this eliminates duplicates. But I hope this explanation at least helped a little bit. So now that we know to sort the input array and we know how to eliminate duplicates, notice, right? So let's say we have a -3. So then the remaining part of the problem, there's only two elements, right? So it basically reduces to 2-sum. And you probably know how to solve 2-sum, right? Obviously, we can put the numbers, let's say that this is our first A, right? So then for the remaining portion, we're basically going to do 2-sum. And you can do that with a hash map or a hash set. But if you've solved the problem 2-sum 2, you know that we don't need to use a hash map. We can use a left and right pointer. So this is our left, and this is our right. And if we find numbers such that left and right added to our -3 sum to 0, then we're going to add them to the solution set. If the sum, though, is too big, for example, if our sum was greater than 0, we want to decrease our sum. Now, we can do that by taking our right pointer and shifting it. So our right pointer would be shifted here. Notice how that decreases the sum because the numbers are sorted. So if you've solved 2 sum 2 before, you know exactly why this works, and I encourage you to watch that video if you want a deeper explanation. Now, on the other hand, maybe our sum is too small, our sum is smaller than 0. In that case, we would shift our left pointer. Because the input array is sorted, if we shift our left pointer, we're increasing the sum. Now, there could be duplicates among these left and right values too. For example, if this 1 was a -3 instead, right? In that case, we don't want to reuse the same element twice, even among our left and right values. So we would not use the same, we would shift our pointer once more over here. We don't want to reuse the same value for left and right either, so we don't get any duplicates. Now, in terms of time complexity, remember we are sorting the array, which is big O of n log n. And then we are not doing the brute force with triple loops. That would be n cubed. We are using the fact that this input array is sorted to our advantage. We're using one loop to tell us the first value, and we're using the second loop to basically solve 2 sums. So we're going to have 2 nested loops, and that's going to give us O n squared. So that means obviously the time complexity reduces to just O of n squared. Now the space complexity will depend. So for the implementation I'm showing, it could be big O of 1 or it could be big O of n, because sorting actually does take extra memory in some libraries. So it depends on your implementation of sorting. It could be O of n. Okay, now let's get to the code.
Should I try to solve it before I look at his code? I think I can. I think I understand what he's saying. Okay, I'm gonna try to solve it. So we'll sort nums. Is that how you sort? I think it is. Oh, this is what I need. Okay, we sort it. Need two loops. We're also gonna need the pointers. I think K is -1. Let me give myself a timer too. I'm gonna do 10 minutes. If I can't do it in 10, I'm just gonna look at the solution. I mean, I practically looked at the solution, but like the implementation, what I'm trying to say. Yeah, I think this is right. Okay, now what? So we have the inner loop, the outer loop, and then we want to check oh, give me 1 second. We also need a result vector. I'm cooked. What am I missing here? So he did mention that the inner loop should be similar to two sums, part 2 or something like that. I think we can do give me 1 second. Yeah, I'm throwing the towel on this one. We're just gonna look at the solution. And I'm not gonna watch the video. I'm gonna watch look at this. Dude, I hate these questions. Okay, let's see. I want to see how he justifies it.
As a list of lists, and remember the first thing you want to do is sort the input array. Next, we want to use each number in the input array as a possible first value. So I will iterate through the index and the value. And remember, we don't want to reuse the same value in the same position twice. So if I is greater than 0, meaning this isn't the first value in the input array, and this value a is equal to nums of I minus 1, that means it's the same value as before. That means we want to continue. We don't want to reuse the same value twice. So we're going to continue to the next iteration of the loop. Next, we're going to use our two-pointer solution for the remaining portion of the array to basically solve two-sum. So we'll have left and right pointers. Left will initially be I plus 1. Right will be the end of the list, length minus 1. Left and right can't be equal, so we're going to say left is less than right. Now we're going to actually compute the sums. So we'll say our three-sum is a plus nums of left plus nums of right. So if the sum is too great, remember, if it's greater than 0, which is what we're looking for, then we need to decrease it, in which case we would say our right pointer needs to be decremented. On the other hand, if it's too small, we need to make the sum bigger. If only I could type today. If it's too small, we need to make it bigger, so shift our left pointer to the right. The last case is if this is equal to 0, so of course we have to add it to our result. So to our result, we're going to append all three numbers. So the numbers are a, nums of left, and nums of right. Now, of course, we got to update our pointers, but how do we update it? There's a lot of ways you can do it, but I'm going to show you the way that you can do it with writing the minimal amount of code. So let me just write a comment to show you a little bit. What if we had the two-sum basically for these left and right, and we were at -2, -2, so -2, 0, 0, 2, and 2. What if our left pointer was here and our right pointer was here? In that case, we found a solution, let's say, right? Then we'd want to update our left pointer, right? So then our left pointer gets to -2 again. But that's the same one as before. So in that case, we want to update it one more time to get it over here, right? Now in that case, now our sum is going to be too big because we're going to be at 0 plus 2. So that's greater than 0. So then our loop is going to execute saying that this is too big, and we're going to shift the right pointer to the left. But notice how that right value is now the same as it previously was too. But that's okay because our sum is going to evaluate as too big, so our right pointer is going to be shifted again. Notice how each value is only going to have one corresponding value that it can sum equal to the target, which is 0. So we only have to update one pointer, and our two conditions up here will update the other pointer by itself. We don't even have to worry about it. So in this case, we're only going to shift our left pointer. Because we don't want to have the same sum, we're going to have to use a loop. So in this case, if nums of left is equal to nums of left minus 1, that means it's the same value, so we have to keep shifting our pointer. But remember, we don't want our left pointer to ever pass the right pointer, so we're going to add that to the condition. So this is all we needed to do. Now I believe, unless I've made another stupid bug,
That one was horrible. Okay, I think I'm gonna stop there. I didn't even get to the hard one. We could look at it, but I think I'm burnt right now. What does this say? Ugh, DP is nasty. Okay. Cool. Okay. I'll do this one next time. Technically, I didn't do the other one either. Yeah. I'll have to come back to 3 sub. Okay. We'll leave it there.